To thank Professor Peng one more time. Thank you very much.
Thank you very much. Thank you.
So it's my distinct honor to introduce our second plenary speaker this morning, who doesn't need any introduction. Professor Federico Capasso is a founding father of the area of metasurfaces, and I'm happy that we started with extension of metasurfaces into quantum realm, but now we're going to hear how transformative a new idea can be when one really thinks about technology-driven applications. Federico, the floor is yours.
Thank you very much for the introduction. I hope the slides are going to show more clearly. Anyway, thank you very much, the organizer, for this invitation. And it's always a nice time to come to Meta, which is really, I sort of consider one of the founding conference, if not the founding conference, after this field started, the metamaterials field. So, let me start with the simplest form of metasurface, okay? These are just pillars here, they're isotropic, and you can basically engineer a metasurface to have a particular phase profile. So what I can do is change the diameter. In this case, it's the only variable that I have, and I can control the actual phase digitally, and so I can create basically a phase library that in this case we try to extend it from 0 to pi. But we can engineer the phase across a metasurface now to create a lens, to create a vortex beam, and this game can continue forever. So then when there's practically infinite possibility, the key thing is to focus on the topics that are of some real physical interest, and possibly also can we translate them into actual technology. So I'm going to actually start from the point of view, I call this a classical type of metasurface. There's nothing quantum here. We just use Maxwell's equation to calculate the actual phase for each pillar. We can project it then to the far field using the Rayleigh-Sommerfeld algorithm, and we can calculate the wavefront, the actually far field in a fairly accurate way. This in particular was done with titanium dioxide, which is one of the favorite materials for nanophotonics. Why? Because the refractive index is fairly high, around 2.5 across the visible, so the light tends to concentrate in these meta-atoms, which has quite a few advantages. And this we developed, we started in this field around 2010, and then we continued to make meta lenses. And these are meta lenses that are realized with the actual Berry phase. Just change the orientation, you can control the phase. So this works in particularly only for circularly polarized light. Then we generalize this, of course, to any kind of incident polarization. And the beauty of metasurface is there are several knobs, okay? You can not only control the polarization, for example, by changing the anisotropy of these meta-atoms and their orientation, but you can also do what we like to call dispersion engineering. So we can control locally the effective index. These are like tiny waveguides, right? So the overlap factor of the field with the meta-atom controls the effective index. So this dispersion engineer is actually very, very, very powerful. And so we have this kind of Swiss nice knob here, and where an area which I'm really not going to go into is that of structural light, where we can generate wavefronts. Essentially, the choice is basically infinite. Again, then you have to decide what to do, something physically interesting or technological, or maybe both. And you know, what has happened over the years, I like to call this system-level miniaturization, okay? For example, this is an example. The objective lens, we don't think that it is a system, but it is a system. It can be up to 10 optical elements, 10 lenses. And in many cases of interest, you can compactify the whole system into a single lens plus an aperture, and you can control with the lens, not only you can control the third order aberration, so you can make a very clean, so to speak, that can control these aberration, the third order metal lens at one particular wavelength. Then you can generate through dispersion engineering, you can make again a single lens that focuses achromatically light across the visible. And in the polarization area, we had I'm going to talk about another compactification here. This is a polarization sensitive camera. It's quite complicated. I'm not going to go into. There's a lot of hardware, sometimes moving hardware. But using a metasurface, we have shown in this paper here, what you can actually do is with a single metasurface, okay, and a lens, and of course you need a CMOS sensor, you can analyze the scene point by point and get the Stokes parameter. So there is a dramatic simplification in the system complexity. So now the question is let's move to actually quantum here. You know, this is a schematic of what a linear quantum optical network is. It's basically a series of beam splitter, mirrors, phase plates, and actually so forth. So, and it scales very rapidly. So if we try to do something meaningful in terms of quantum information process to easily occupy this actual space here. So the question is, can we compactify all this functionality in a single metasurface? That's why I talked about it, and we have addressed this in this paper here, called this quantum metasurface, if you wish. Now, before I move over to the real quantum, I want to say that metasurfaces are commercially available now. They are in cell phones, in other gadgets, and it is expanding rapidly. I started this company, MetaLens, with my postdoc, Rob Devlin, who is actually going to give a keynote in this conference here. And the idea behind it is because we can make metasurfaces with the same technology by which we do integrated circuit chips, then there is a convergence, particularly in the actual smartphone, of electronics and actual optics. And this convergence is very powerful, and it's going to expand more. So basically, you know, if you know how the pipeline is for making chip, the real difference here is instead of an electronic design file, there is an optical design file. This you can see is a 12-inch wafer, which 7,000 meta optics, okay, and the companies that work with MetaLens are initially ST Microelectronics, and then UMC currently to essentially do the manufacturing. And you know, this you can see, for example, they're in cell phones already, in fact, and look at the compactification. Typically, a camera module for a smartphone contains several plastic lenses to correct the aberration. Here is just a single metal lens, and actual aperture does the job. In particular, this uses amorphous silicon metasurfaces for face recognition system using an array of dots, you know, hundreds of them that to do the face recognition. And again, the key point is a partnership with the major foundries. And you can see here, in fact, several groups have they specialize in tear downs, essentially reverse engineering products, and they have quickly figured out, you know, where some of this stuff is, you know, without me having to actually explicitly saying it. Okay, and this is one example here. And the other very exciting is the development of alternative forms of face recognition. It's so secure, face recognition, that we don't tend to think about the actual cases where people can still go through. So who cares? Well, the actual companies care, right? They can't have a bad publicity that 1 out of a million can actually get in the iPhone or so. So there has been a push to do more secure ways of recognizing. And the system, and here the basic research was done, in fact, in my group at Harvard. We published a science paper in 2019, and now this system of polarization-based face recognition process is being developed by Metalens. The general platform is called Polarize, and particularly for face recognition, can use for different type of things. Polar ID will come to market this year, and essentially it is based, it's here, it's based on the idea that you want to take 4 images of an actual object. This is a face example, and then you overlap these images, and then of course there is a lot of pipeline for software and so forth, but at the end this is essentially cannot be spoofed, this system of face recognition. So it is very powerful, and we are particularly proud to say it took record time to go from science in my group to commercialization, 6 years basically. And I want to go now to the other slide. I showed at some point, we have this compactification of system from complex to less complex, so maybe just one meta surface, one meta element. Now, what are we going to do with quantum optics? Well, here there is quite a few challenges. Okay, the superposition in linear, what are the resources in linear quantum optics? Is the superposition and interference of photons, that we all know. And the system to manipulate them in linear quantum optics is a mesh of beam splitter and phase shifter, mirrors, and so forth. So this essentially, what does it do? It implements a unitary matrix to do the kind of quantum information process that you are interested in. And so this linear optical echo is basically a multi-mode interferometer. Remember this point, okay? We're talking about the superposition and interference of photon. So it is the basic resource behind quantum linear optical quantum computing and quantum communication protocols. But there is a problem, that is the scaling, okay? We have a unitary here, and has of the order of n square independent elements, okay? So the bottom line is you need to have n square typically beam splitters and phase shifter. So there is a tremendous increase in the complexity going from my screen here, let's say, to this space here very, very quickly. So what we are interested in, so the chip footprint, it explodes, the loss accumulates, phase stability is fragile. So what we need an architecture where we break this constraint of this n square constraint, basically, and so that we can get the advantages of interference for free. By for free, I mean without adding this tremendous amount of hardware and so forth. And so this is, it quickly kind of scales up. You can schematically show this interferometer this way, okay? And this, if you like, maybe slightly more realistic, but it gives the message that I just said before. In fact, this is a very impressive realization in terms of a real first, which shows at the same time, because of the performance, what the potential is of quantum information process, but at the same point also how unmanageable it becomes for technology type of applications. And so we go back to the actual basics, which is the famous Hongu-Mandel type of experiment. And essentially I have a beam splitter, a 50-50. I come in with 2 photons, 2 identical photons, and I can control the delay between these 2 photons coming in, and I have these actual outputs. So what are the outputs quantum mechanically? This is the unitary that represents the beam splitter here. And so you see there are various terms here. Now the point is this, there are these, I call them magical quantum quantum cancellation, which Richard Feynman, that's in this context, he said, you know, no one understands quantum mechanics. Well, we can understand the algebra behind it, okay? You see these terms here, okay? They cancel each other. That corresponds basically to a photon coming out at one port and the other photon at the other port and so forth. But it can go in two different ways, through to reflection or to transmission. There is a minus sign here because there is a 180 degrees phase shift between these two diagrams. So they actually cancel out. So lo and behold, here's the magic. You have two photons. They always stick together, photons. They either come out here or they come out here, and you can plot the coincident probabilities of photon pairs. Here, this is a famous Hongu-Mandel dip. Okay, so it says basically there is, if you do things right, a negligible, ideally zero type of probability of a photon coming out, you know, from simultaneously a photon coming out from this port and this. This is a very deep result, you know. By thinking about this, I said this is a powerful statement here, that the correlation of quantum mechanics are stronger than any classical type of implementation or model can give you. This goes at the heart of the Bell inequalities, basically. So by understanding better Hongu-Mandel, I said, now I understand what this inequality means physically, you see. This is what John Bell tried. He tried to do essentially a hidden variable theory of correlation of this type, not particularly this experimental here. And you saw there is no way around it, okay? There is no way that you can come up with a hidden variable description of these quantum results. So it's an extremely strong thing, and probably this is the really distinguished feature of quantum mechanics to reveal this type of correlation like shown in the Hongu-Mandel. Now, if I were in a classical setup, I would see a horizontal correlation plot here at a coincident probability of actually 0.5. So now we can do this experiment in a slightly different way, and we'll understand quickly why. We can use two photons of different polarization, horizontal and vertical. We can implement a unitary transformation here to go from a polarization basis this way, vertical and horizontal, to diagonal and anti-diagonal. Then we can do the same thing as before, same type of argument. Okay, we can calculate the coincident probabilities of photons at the actual two output here. So this is the rotated basis, you see, from vertical, horizontal to diagonal and anti-diagonal. And again, you see here this magic, as I actually called it, that these terms here, okay, that correspond to one photon, horizontal photon coming out in one port and a vertical one here, cancels out this term here due to this minus sign here. Okay, so you're left just with two photons at the output here or actually here. And this is the typical, both calculated and experimentally. Today we can get very close agreement to what the expected theoretical dip is. And so now we are doing the contest of the metagrading. Remember, I showed you, I mentioned this paper here. This paper is a significant paper because it's a generalization of Fourier optics, which we call matrix Fourier optics. So what's the key point? You know, if we have a regular aperture, this is an aperture in the language of Fourier optics, what does the far field look like? The far field, this was obtained in some very early papers by Joe Goodman, who is the father of Fourier optics. Okay, what is the far field? The far field is a plane wave expansion, where the coefficients are basically scalar. The key difference here, we cannot use this language because the aperture, we can use part of this language because we have this polarization sensitive element. So what happens now is that the far field is still a Fourier series of plane waves, but the coefficients are now Fourier transform, as you see here, of the actual Jones matrix, okay? And this is so what we can do then is the following, you see, if you have followed me, okay, that now every diffraction order, you see, because it depends, you know, on this Jones matrix that you show here, then in the far field you have to take the Fourier transform, okay, act as virtual analyzers, okay? That's what we are aiming at, okay? We want to make a metasurface where these acts and analyze. This is a powerful way to think about it because it abstracts from the device type of implementation from the hardware, and it says the actual function is obtained is a diffraction order. By that I mean what? This is an optical element. For example, if this diffraction order encodes for a particular polarization state in the actual far field, it means that if I do an experiment and I enter here with a polarization corresponding to the diffraction order of interest, it follows Malus' law. It means if I rotate the incident polarization by 90 degrees, I will see that the intensity in this designer diffraction order will act like an analyzer, so it will go to an actual minimum. And that is very powerful because now we can, in this way of thinking of diffraction order, we can think of diffraction order as elements that implement by design certain quantum mechanical correlation. And that's the potential power for quantum information processing. So basically, what are we going? This is actually going to be a meta-grating because this is a metasurface. So a metasurface will have only the zeroth order. But by making it into a meta-grating, by repeating, I can have multiple diffraction order, like is actually shown here. Okay, and in the experiment, so we want to do, we come in with as nice pure state as we actually can. And we have photon detectors here, single photon detectors and correlation type of electronics. And so what is the aim of this work? And in this paper that we published in 2025 is to generalize the on-demand interference to multi-output modes. And so on-demand engineering the quantum correlation landscape. We don't have yet a compelling type of application that we can demonstrate, but I think the vision is a pretty interesting one, and it will definitely lead, in my opinion, to somewhere interesting. So what we did essentially here, we implemented this version of the Hongu mandel with an actual metasurface here. Okay, so the effect is actually the same. So there is quite a bit of engineering, meta-engineering, I should say. And in fact, one solution is that we decided to have the two diffraction order. They're implementing diagonal and anti-diagonal analyzer in the far field. You see here, one is diagonal, this is anti-diagonal. Each has its own phase, and the output, as expected, is exactly like you would observe for a Hongu mandel setup. There is a subtlety here, which is important in the actual design, okay, that you have to make sure that the majority of the light actually goes into these analyzer, I call them. So this analyzer will never have, you know, the kind of suppression ratio of 5 orders of actual magnitude of real or stuff that you can actually buy from Tor Labs, wherever, you know, Edmund Optics and so forth. They maybe have 10, 100, but that's enough, okay? So there is always going to be some light going in other orders, and that will affect the actual visibility, but that can be engineered. That is my point. I mean, we have seen this over and over. When we started to play with meta lenses, people used to tell me, Federico, you're never going to get to an efficiency higher than 20% because light is going to go everywhere. I said, wait a minute, it's not going to go everywhere. It's going to go where I want it to go. And in fact, I can tell you that the metasurfaces made by Metalens now have high efficiency for face recognition. These are of morphosilicon. So we can take under control potentially this visibility problem to enhance it. And well, this is... Now the powerful thing is this: you can view this correlation in terms of graph theory, and it's something that my student really was pretty brilliant in figuring out. Okay, so two nodes that are connected by solid line represent the entanglement. Okay, and by the way, what really controls the overlap of these, okay, in this case, if you like, a situation of perfect type of entanglement and so forth, is a so-called Hilbert-Schmidt inner product. It's a complicated name for something simple. It represents essentially the product of actual matrices. Okay, so if the product is actually zero, okay, there is home type of entanglement, okay, and if it's non-zero, there is partial or disentanglement. So that also adds an interesting engineering twist to these metasurfaces, and this is what it is. And so you see, this is a point that you see, this is now this design. We can represent, we can take the simply linear home type states. I'm going to discuss briefly this one. We can make square states and so forth. We can make we can introduce actually a diffraction order which has a matrix that is not orthogonal to the others, okay? So in this case, what you see here, you have this partial type of entanglement shown by this dotted line. There is still some quantum correlation, okay? So these weighted quantum graphs can be very interesting. And we did two things, okay? We did this here. We did this. I'm going to show you preliminary results. Unfortunately, I was hoping to bring them today, but the student just didn't make it in time, with 8 orders of diffraction. So it's a matter, of course, to study these polarization, these orders of diffraction, again, these analyzers, and see how they analyze light. So we did the Mueller matrix polarimetry on these to identify correctly that indeed we were obtaining this, okay? And in the experiment, you know, we use a standard photon down conversion to create the actual photons, okay? There's a standard setup here, and we can control the actual delay line, which is important to get that famous dip. Here we have the metasurface, or we have as a reference polarization beam splitter, and then our single photon detectors for studying the correlation. And this basically shows you, I don't have time, I would have to spend 10 minutes to show you this, but the key point is this, okay? You observe clearly the Hongu-Mandel type of interference, okay? For one here, one color, purple represents for the polarization beam splitter that replaces the metasurface. The black is for the actual metasurface. So you can see clearly here the correlation between +1 and actual 2. This is this device here, which has 2 designer diffraction order, then 4 designer diffraction order. You can get between opposite color, you can get the dips, okay, and that is good. But then, you know, in the other ones, what does it mean? That I can now get single photon appearing simultaneously in both orders. There is still a correlation. We call this an anti-correlation, okay, and this is interesting. And so basically, this is the full story here. You can clearly see that we get a visibility. Clearly, we are below the actual classical line and so forth. And when we look at -1, for example, and +2 here, okay, we actually can get, +1 and +2. We can get an anti-correlation. Okay, so So, you know, this is, we can reduce now a Hadamard interferometer to a single metasurface, basically. These are the matrices that describe them. And I think the approach is actually quite powerful. Why? It essentially circumvents the n-square scaling. That's the most interesting thing technologically. Now, I just want to spend the last 2 minutes because I said I really would like to show something really new here, and 8 orders of diffraction. So my student was hard at work to try to get it done. And let's see. So this is basically the Mueller matrix polarimetry. You have a laser source. You can control arbitrarily the polarization by this combination here, right? And then you have essentially a signal coming in. You're looking at signal all this fraction order, and you can do full Stokes polarimetry. Okay, and the key point again is the deattenuation. Deattenuation is a complicated word for something very simple. It's the suppression ratio, as described. Again, we cannot reach the one suppression ratio of commercial thing, but we can get to values that are, you know, still very quite close to actually 1, and so useful for what we want to do. And this, in fact, is this is what the deattenuation is. Again, it's the and so what we do essentially, we come in this case, with 90 different polarization state, and we actually measure where we end up in the Poincaré sphere at the output. That's the main thing. And in fact, these are the results. You see, 8 diffraction order, really very, very nice, okay? I'm going to show you now what the values of the deattenuation is, okay? So again, these are the designer polarization state, you see. 4, if you like, diagonal, 4 anti-diagonal, and this gives you a visual way to see this. And in fact, this you see are the values of the attenuation experimental one. This is pretty good. We can do, it's a more complex than a simpler 2-port type of devices, but the attenuation is uniformly high and close to unity, so we can really do useful quantum information processing with this kind of deattenuation. What's lacking is, I flew yesterday in, he didn't have time to measure the correlation, but I'm sure that tonight he might call me and say, Federico, I have the results. Unfortunately, I will not be able to show them to you. So what are the conclusions? The conclusion, we've introduced a graph-based metasurface platform. Now this is not just, you know, when he came up with this thing, I said, okay, fine, we use a way to represent symbolically. But then he said something very interesting. You see, Federico, but now we can design some arbitrary graph, right? Without thinking what implementation is, and then ask, and how then can we design the metasurface? So this inverse approach is as useful, if not more useful, certainly for invention, than the approach, say, once I decided to implement something, this is the graph. The other way is more abstract. Let's play with this strange graph. What can it do? And what is the metasurface that we need to design in order to achieve this? So there is this dual point of view of using this quantum graph. So the key point is we can compress a room size, and this is literally, I've shown you the room, the full lab full of equipment, interferometry into one metasurface, essentially breaking this scaling that as such, linear quantum optics is not useful for any practical technology. And so, you know, it means that we can have even potentially a scalable, portable, certainly scalable, compact, and potentially portable route to quantum information processing on a chip. That's the idea. This example, we have compressed a quantum information process functionality on a single chip. Okay, essentially a network compressed into a single chip. And for the future, we are developing a new protocol, for essentially the heralded generation of Greenberg GHZ states, okay, and cluster states using a single metasurface device is a new chapter, really. And in the long term, I think this could open the door to flat-free, free space, quantum photonic architecture for these three important areas, and including the deployable platform. That I mean, you know, if we want to deploy them on a satellite, on any drone, we have to break that scaling so we can put everything on an actual chip. So ultimately, it goes down to the same vision at the beginning. The flat optics allows you to do, using fabrication technology of electronics for chip, for actually optics. And this convergence we are just starting to explore now. It's a new way to think about it, right? There's no more separately optics with all its things, you know, plastic lens and electronics, but there is only one fabrication technology. So I think, and I want to acknowledge my graduate student, Kerolos. Marco D'Alessandro was an undergrad student. Neil Sinclair is a research scientist in Marco Lonca's group, great collaborator, and finally Matthew Ye, who joined our efforts recently. Thank you for your attention.
Thank you. Thank you. Thank you very much, Federico. So we are ready for some discussion before the break. Yeah, go ahead.
First, thank you very much for the very nice and wonderful talk. So your talk is about quantum computing, but my question is more about the optical computing in classical way. The optical computing is very hot in recent years. Can you comment on the potential of metasurfaces applied in classical optical computing? Because in this area there are still many problems unsolved, but metasurface is kind of diffractive optics. In your case, can you comment?
Yes, I don't know how much I can add to what you said. First of all, you know, our quantum computer here, not mention anything about quantum computer. What I said is this technology that we demonstrated can be a basis to do quantum computing in a compact way on a chip. That's all. We still need to do it. Now, in terms of, you know, it's interesting you mention optical computing. I spent 25 years of my career at Bell Telephone Labs before coming to Harvard, and there was a hot debate then. And at some point, Bell Labs concluded, and I don't consider this as an endorsement of what I'm going to say. I'm just to tell you a conclusion by a number of very smart people who thought deeply, and they said, it's not going to go anywhere. We are wasting our time. And after 10 years, they killed the thing. And the argument was that following bottom line to this, you know, which I tend to sort of favor, being a practical guy, and you know that there'll be a lot of photons in the system. Look, space division multiplexing with all these racks, a lot of photons flying around, but the computation will be done electronically. There is such a huge distance yet between what it is now, right, which is very powerful, look, and it continues to improve, and optics coming in to say, now we are going to do the CPU function is going to get done by an optical computer. I just don't believe it. Now, I realize that say I don't believe it is not a very scientific argument, but it's based on the opinion of many people I've listened to, that I've read, so I think it's a tall order. I would love to succeed it. You know, you have to beat the actual competition. It's more than just demonstration. There have been many demonstrations. They always have actually failed. And I think even what's proposed now, again, we have to confront the real world of these powerful electronic computers that are improving, constantly improving. So that's sort of my assessment. I'm sorry I can't be more positive. I would love to be wrong, by the way, okay? I would love to be wrong.
So Federico, always interesting. So I'm interested in the graph theory and then the engineering of it. And I'm just wondering what it tells us about if we take partially coherent states, can it be used to sift quantum coherence out of that in different ways?
Yeah, this is a very interesting way. In fact, I think what you just did describing like a coherence filter, essentially, do some filter reaction. We have thought about, not really a lot about this line of research, but there's so much to do that we said, but yes, because you can absolutely control, you could use squeezed light, for example. Why not use squeezed photons, right?
Or can you pull squeezed photons out of thermal or partially thermal states?
That's a hard one. Out of thermal states.
So the key question I think I have on that is, do you have to improve the contrast of these to be able to really get into those sort of areas?
Yeah, I think that's definitely true. Even though one has to admit the contrast that we obtain, particularly some published data that I showed you, it's pretty good, right? 8 orders of diffraction, we are really close to 1. Now, it's not the 10 to the 5 of a commercial analyte, but you don't need it. In fact, we showed it for our polarization camera. You don't need that extreme type of de-attenuation.
I think that's true for those applications, but if I'm trying to sift...
No, I know, absolutely, because you are right, because when you are talking about, and I completely agree with you, when you are talking about what you say, is basically, since it's about the correlation and it's about the phase, you know, right? I think being able to do would mean achieve a significantly higher the attenuation. I hope not the 10 to the 4 or 10 to the 5, you know, that's really extreme, I think.
We'll take one more.
Yeah.
Hey,
so,
hi, Girsch.
Hi. So it's so wonderful that you can solve the problem of using the n-square linear optical elements by using a single metasurface. I was wondering if you have thought of producing noon states with number of photons more than 2.
Yes, but it's something that I don't have a slide. Yes, we have thought about it. It is possible to create all kinds of different states. In particular, the interesting states are the one in which at some point I showed like a matrix of connected dots by solid line. But if you saw there was one in which there was actually a dotted line, okay? That dotted line creates partial entanglement because that is going to be implemented by a matrix that is not orthogonal to the other matrices, okay? So you can engineer the entanglement, you know, partial entanglement and so forth. You don't always need a complete entanglement. There are interesting type of applications. So you can create the complexity of states that you can create by using those dotted line is remarkable, really. Whether it leads to something useful, I don't know, but certainly we want to explore it. And thanks for the comment.
Mm-hmm. Let's thank Federico one more time and all the speakers. Thank you. And thank you very much for being here for this session. We are now heading for the poster one.
Thanks very much. Coffee and posters.